squeak's not too bad. At least I got colors. All right, so I thought it would be productive for me to work out a example that's kind of like some of your homeworks. There's a lot of stuff in Chapter 1 that I didn't write. You need to read my Chapter 1. There's a lot of material there that, I just don't have time to put all on the board in class. But one of the things probably be helpful for us to work out is just an example. So suppose you want to solve sine of z equals to 2. Now, in the notes I mentioned, I have, like if we had sine of z equals to 0, you could work that out, right? And in fact, the answer is just integer multiples of pi. But of course, in the real case, so like if this was the real sine function, well, it'd be hopeless, right? But let's see here. So this sine z is what? It's sine of x plus iy, right? Equal to 2. And it turns out that sine satisfies the addition of angles formula. So if the question is just to do this calculation, you can do as follows. This is sine of x cosine of iy plus cosine of x sine of iy. Right? So cosine and sine and Cauchy and sinh are intimately related. They're very, very closely related. So cosine of iy, 1/2 e to the iy plus e to the minus iy. Right? So what is that? That's e to the 1/2 e to the minus y plus e to the, e to the y. Right? What is that? Well, that's Cauchy. That's exactly just hyperbolic cosine of y. All right. And sine of iy is 1 over 2i e to the iiy minus e to the minus iiy, which is 1 over 2i e to the minus y minus e to the y, which is I times 1/2 e to the y minus e to the minus y. Now, remember 1 over I is minus I. So when I flip the 1 over I upstairs, that brings out a minus, which then I distributed through to change the signs on the terms. That's what happened there. But this is straight up I sinh of y. Right? And while I have just done these calculations for real x and real y, well, for real y in both of these actually, right? It is worth noting that we have a theorem. This is worth knowing for future reference. If you have cosine of iz, it's the hyperbolic cosine. Oh man, it came right there. Audric is like, exactly, you shouldn't use these boards. Cosh of z and sine of iz is I sinh of z. So the identity I just worked out above for y being real is similarly true for complex z. Right? I'm just saying something you should be aware of. All right. Of course, if I already knew what I wrote in blue, we could have made quick work of this, right? We would have gone straight from here to sine x cosh y plus I cos x sinh y equals to 2. All right, now how do I solve that equation? This is a complex equation. The only way it can be true is for both the real and the imaginary parts to both be simultaneously equated, right? So I have, on one hand, sine of x cosh of y equals to 2, and I also have cosine of x sinh of y equals to 0 from the real part, from the imaginary part. So the second equation is easier for me to analyze than the first, because the second one, the only way that can be 0 is if either cosine of x is 0 or sinh of y is 0, right? So two cases, right? Sinh of y equals to 0 or cosine of x equals to 0, right? Sinh of y equals to 0, that's very nice because sinh is an increasing function everywhere. Sinh of 0 is 0. In fact, that's the only 0 of sinh. So this implies that y is equal to 0. Once you know that y is equal to 0, what's the first equation become? Well, the first equation becomes sine of x cosh of 0, right? Equals to 2. Cosh of 0 is just 1. So we get sine of x equals to 2 for real x. As we know from trigonometry, there are no solutions. All right, x is a real variable. We know that the sine of a real variable is bounded between -1 and 1. There are no solutions. However, cosine of x equals to 0, that tells us what? Yeah. So x could equal to pi over 2 or 3 pi over 2 or da-da-da-da. In fact, x is an element of pi over 2 plus 2 pi z unioned with 3 pi over 2 plus 2 pi z. There are two infinite families of solutions of cosine. In other words, any odd integer half multiple of pi makes cosine 0. You could do that. But on the flip side of things, sine of such theta is 1. Over here, sine of such theta is -1. So the first family are the ones that make sine be 1. The second are the ones that make sine be -1. And so, okay, great. Cosine of x being 0 solves the second equation, but what about the first? Well, the first equation, then I have to go back to the first equation, right? So if x is an element of pi over 2 plus 2 pi z, right, then sine x cosh y equals to 2 becomes what? It becomes 1. It becomes just cosh y equals to 2, right? Which is fine. Cosh of y can be 2, right? And so y is equal to inverse hyperbolic cosine of 2. So on the other hand, if x is an element of 3 pi over 2 plus 2 pi z, then we get cosh of y minus cosh of y equals to 2, which is impossible for real y. So the answer, it turns out, it only includes the pi over 2 plus 2 pi z type x. And so anyway, the answer is z is an element of pi over 2 plus 2 pi k plus I times the inverse hyperbolic cosine of 2, right, such that k is an integer. There you go. That's the answer here. So in your homework, you have like solve sinh of z equal to I. This is the kind of approach you need to take. You need to break it into real and imaginary parts and deal with what happens there. Right? And the critical things is you need to know what are the zeros of sine, what are the zeros of cosine, what's the range of sine, what's the range of cosine, what's the range of cosh, what's the range of sinh in the real sense. it turns out that those things don't, I mean, it is still true that, like, here's the kind of surprising thing a little bit. Sine of z equals to 0 if and only if z is an element of pi z. So there are still some things that are like true. They're still to continue to be true. The only zeros to sine are integer multiples of pi. The only zeros of cosine are exactly the ones we wrote down here. That's also true for complex cosine, complex sine. But other things that we know from real analysis fail to be true. Like the magnitude of sine and cosine is bounded by 1, right? That's not true for complex sine. We just found z that makes sine of z equals to 2. That means the magnitude of sine z is 2. So the magnitude of complex sine is no longer bounded by 1. It could be as big as you like, all right? And of course, there are other ways you could come to that understanding. Like, what is the complex sine function if you write it in terms of, it's, I'll just do this much more for today, and then I'll stop with this stuff here. But like sine of z, well, I already wrote it right there, right? Sine of z is, well, it's right here, right? Sine of x, cosine, rather cosh y, right? Plus I cosine x sinh y, right? So what is the modulus of sine of z? It's the square root, right, of sine squared x cosh squared y plus cosine squared x sinh squared y. And there's no reason that that has to be small. Like you can choose the x, which makes sine of x 1. I mean here. So if, for example, if z is equal to like, x plus iy with x an element of integer multiples of pi, then of course sine of x equals to 0, right? Cosine of x is equal to plus or minus 1 in that case. And in this particular context, the modulus of sine z is the square root of, well, plus or minus 1 squared sinh squared of z, of y rather, right? In other words, it's the absolute value of the sinh of y. And the absolute value of the sinh of y can be absolutely as big as you want it to be. So as you can see, the modulus of sine z is not bounded. It can be as big as you want it to be. Anyway, there's that. All right, so, excuse me. That brings us to chapter 2. And so here, with section 2.1, we're going through a review of basic analysis, all right? And so I'll just say, like, at the start of this section, we have definitions of what's a complex sequence and properties of complex sequences. I'm going to try to go through this very, very quickly. We will eventually come back to using sequences for things, but for the most part, we really don't use the sequence stuff that much until later. Primarily, we need the sequence stuff when we get back to, studying series, because series, you can't understand series without sequences, right? But here it is. So here's just what we're doing is analysis over the complex numbers, all right? So definition, A mapping from, say, the natural numbers to C is a sequence, right? We say the limit as n goes to infinity of, we usually typically use the notation a sub n, right? A sub n is equal to L. So the limit of a complex sequence is L, if and only if what? For each epsilon greater than 0, there exists big N in the natural numbers such that little n greater than or equal to big N implies that the modulus of a sub n minus L is less than epsilon. Yeah, this should be the same as real analysis, but the picture here is a little bit different, right? So the picture we should have in mind is the complex plane. So there is something else, there's something different going on here, right? So like if this is the limiting value L, right? What this is saying is if you look at an epsilon disk, right? Because if I look at the modulus of a sub n minus L, that's saying the distance between a n and L is at most, at most epsilon, right? So there's this epsilon disk, right? So here, epsilon disk, right? And what do the a sub n's look like? I don't know. I mean, let me picture them as dots, if you will. All right. So like maybe a sub 1 is over here. I don't know. Maybe a sub 2 is over here. Maybe a sub 3 is over here. It doesn't really matter. But the point is, eventually, right? The a sub n, maybe out here is a sub n minus 1. Okay. But eventually, as you go far enough in the sequence, you can capture the tail of the sequence inside the epsilon ball. If you just take n to be large enough, they eventually have to zoom in closer and closer to the limiting value. Right? This is what it means for a complex sequence to converge to L. Just like in the real case, they have to like kind of cluster around that point in the number line, right? But okay, so complex sequence. So what's a bounded sequence? Actually, let me not write it down. A bounded sequence is simply a sequence that, if you look at the, what's the word? The absolute value of the sequence, if it's a real sequence, or the modulus of the sequence, if it's a complex sequence, such that you can find a specific number, positive number, which is larger than the absolute value of the sequence overall. In the case that this happens, we say it's a convergent sequence, right? A convergent sequence. This is called a convergent sequence. And if S sub n and T sub n are both convergent sequences, then you have S sub n plus or minus T sub n, S sub n times T sub n, and S sub n over T sub n, all convergent. Although, of course, the quotient one, I'm assuming what? I'm assuming that the T sub n's are all non-zero for it to be well-defined, all right? And in fact, what do they converge to? This one converges to S plus or minus T. This one converges to ST. And this one converges to S over T, provided, Tn is not equal to 0 and T not equal to 0. And here I'm saying where Sn converges to S and Tn converges to T as n goes to infinity, right? That's our other notation for sequences. We don't have to use the limit notation. We can also use, like in a sentence form, we can say the sequence goes to the limiting value as n goes to infinity, right? That's a freedom we have in how to express the limits. But the limit should be expressed somewhere. Of course, for a real sequence, right, you also have the squeeze theorem. Remember? Squeeze theorem? No? If Sn, Tn are from natural, excuse me, elements of the reals, and Sn less than or equal to, let's say, I need a middle sequence. Oh, curses, I used R here. So Rn, Tn, the reals, and Rn is less than or equal to Sn is less than or equal to Tn, right? Then if, the limit of Rn equals the limit of Tn, then the limit of Sn is also equal to that same value. That's one version of the squeeze theorem. It gives you the existence of the middle sequence, the existence of the limit of the sequence. Now, if you know that the limit of the middle thing exists, and you know the limit of the Rn and the Tn both exist, but they're not equal, then the theorem gives you a slightly less interesting thing, which says that the limit of the middle sequence the value of that limit has to be between the limits of the lower and the upper sequence bounding the middle one. This is the squeeze theorem. Again, the stronger form of the squeeze theorem gives you the existence of the middle limit, but that only comes when the upper and the lower things match up. All right. So let's see here. What else can I tell you? A big theorem, bounded monotonic sequence of real numbers converges. So what does monotonic mean? It means it's strictly increasing, or it's either increasing or decreasing. I think you need strict increase or strict decrease. Well, sequence of real numbers, so a function from naturals to reals. So that's a big theorem, the bounded monotonic sequence theorem. Furthermore here, definition, if an is a sequence and then a subsequence of a sub n is sequence of form a sub nj, where j maps to n sub j is strictly increasing function of j. So, for example, right, you could have a sub n equals to minus 1 to the n, right? This is a sequence, right? There's oftentimes the subsequences we like to look at are, in this case, n sub j equals to 2j, right? Or you could look at n sub j equal to 2j minus 1, right? So basically, you're looking at a sub 2j, which is what? Minus 1 to the 2j, also known as 1, or a sub 2j minus 1, which is minus 1 to the 2j minus 1, which of course is minus 1. So this sequence, it oscillates between plus or minus 1, right? We can look at the subsequence of all even terms. We just get the constant sequence 1, 1, 1, 1, 1. Or we can look at the subsequence of odd terms, and we get the constant sequence minus 1, minus 1, minus 1, minus 1. All right? So definition. Let A be n be sequence. And we define lim sup, limit superior of a sub n, to be the upper bound of all possible subsequential limits. Likewise, lim inf, the limit inferior of an is equal to the lower bound of all subsequential limits. And in the upper bound, if there is no upper bound, we say it's infinity. If there is no lower bound, we say it's minus infinity. Those are both possible. So like in my previous example, the lim sup is what? It's just 1. The lim inf is minus 1. All right. And so like the point of the subsequential limits, like looking at sequences, subsequences of sequence, it's mostly a tool for proving the limit doesn't exist. Okay, because the theorem that we get next from this is that theorem, the limit of a sub n is equal to L if and only if the lim sup of a sub n is equal to the lim inf of a sub n is equal to L. In other words, the sequential limit of a sequence exists and is equal to L. And this is, and to be clear, these things I'm saying right now are really intended for real sequences, okay? I mean, you could talk about subsequences of a complex sequence for sure. But certainly when we talk about bounded monotonic sequence, and lim sup and lim inf, this is, here we have in mind at the moment a real sequence. So this is theorem 2.1.9, if you want to see it stated slightly more carefully. All right, so now let's turn to complex sequences. I mean, I've already told you a little bit. These theorems here about the sum and product and quotient, these are true for complex sequences. You know, however, whenever you write an inequality, then we're talking about a real sequence, because there's no inequality for complex numbers. All right? So, theorem. If Zn is equal to x sub n plus iy sub n for n in the natural numbers, in other words, we've got a complex sequence, right? And if Zn, let's say, goes to z, which is x plus iy, right, as n goes to infinity, right? Then the sequence, well, excuse me, I shouldn't say and. I'm an idiot. And z, just forget that. And z is equal to that. My bad. Oh! So sorry, guys. And z is equal to x plus iy. All right. Then Zn goes to z if and only if xn goes to x and yn goes to y, as n goes to infinity, of course. So to determine the convergence of a complex sequence, we can look at its real and imaginary parts and see what happens to each one of those. All right. Here, I'll do the forward direction of the implication here. Suppose Zn goes to Z, all right? N goes to infinity, right? And then consider, absolute value of xn, or absolute value of xn minus x, right? Is less than or equal to the modulus of xn minus x plus I times yn minus y. See, because this is just a basic property of complex numbers, right? If I take a real number and then I add an imaginary piece to it, it is longer as a complex number than the original just real number, right? This should be geometrically just obvious. Anyway, so what is that? Well, this is straight up the modulus of z minus zn. Or rather, zn minus z, my bad. Right? And the thing is, we know that the limit of zn goes to z, right? So we can make the modulus of zn minus z as small as we like by choosing n as far out as we want. So this inequality straightway implies that the limit as xn minus x is equal to x. I mean, that xn goes to x, right? So, I mean, to complete it, if epsilon is greater than 0, choose n in the natural numbers such that, n greater than or equal to n implies modulus of zn minus z is less than epsilon. Hence, modulus of xn minus x, which is less than or equal to modulus of zn minus z, is less than epsilon, which implies, of course, that the limit as n goes to infinity of xn is equal to x. A very similar argument gives you that yn goes to y. Okay? The converse direction, would be something like this, right? If xn goes to x and yn goes to y, let epsilon be greater than 0. Choose n, say nx and ny natural numbers such that n greater than nx implies the modulus of xn minus x less than epsilon over 2, and n greater than or equal to ny implies modulus of yn minus y less than epsilon over 2. We can do that because we're given that the limits of xn and x both exist and are equal to x and y respectively. Then let n equal to the max of nx and ny, and note for n greater than or equal to that n, we have what? Well, we have modulus of zn minus z, right? Which is equal to the modulus of xn minus x plus I times yn minus y, using the notation introduced in the proof. Well, that, by the triangle inequality, is less than or equal to the absolute value of xn minus x plus the modulus of I times yn minus y, right? But the modulus of I times a real number, we can just get rid of the I, right? By the product of using the product rule for absolute value, for modulus. So this is really just the modulus of I. What I'm trying to say is modulus of iz is just equal to the modulus of I times the modulus of z, right? Which is equal to the modulus of z again. And here I don't really mean z, I should use a different letter, but I'm taking z to be like y, anyway, by this property here applied there, we have, I can just basically erase the I, right? That's my point. And then this is less than epsilon over 2 plus epsilon over 2, right? And not less than or equal to, actually strictly less than, which of course is less than epsilon. Thus, the limit as Zn goes to Z exists and is as claimed. Okay? So that is why we can trade a complex limit for a pair of real limits. Definition. A sequence, A sub n, is Cauchy if there exists n in the natural numbers such that n comma m greater than or equal to n implies the modulus of A sub n minus A sub m is less than epsilon. For each epsilon, I should say. My bad. So this is a Cauchy sequence. Definition, a space is complete if and only if every Cauchy sequence, good grief, I can't. Every Cauchy sequence converges. All right. So it is always true that convergent implies Cauchy. All right. But Cauchy implies convergent is only true in a complete space. Do you guys know an example of a space which is not complete? The standard example I give students is this. If we look at the space of rational numbers, right? If we look at the space of rational numbers, a sequence of rational numbers that's easy to form is truncated decimal expansions of the square root of 2. Right? So this is what? 1.41 dot, 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 right? So I could look at the sequence 1, comma, 1.4, comma, 1.41 dot, 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 right? That is a sequence of rational numbers. But it is not convergent in the space of rational numbers because the thing it converges to is what? Right, so if this is A sub n converges to the square root of 2, which of course is not an element of the rational numbers, right? So this proves that the rational numbers are not complete, all right? In contrast, the real numbers are complete, and the complex numbers are complete. So we can test for convergence by checking if the sequence is Cauchy. If the sequence is Cauchy, it's automatically convergent because complex numbers and real numbers form complete spaces. In fact, one way you could construct the real numbers is to take the rational numbers and adjoin to them all limits of Cauchy sequences. This is called the completion of the space. So the completion of the rational numbers with respect to the usual notion of distance, usual Euclidean norm, absolute value, if you will, is the real numbers. There are other norms that are possible to give to the rational numbers. There's something called the p-adic norm. And if you take the completion of the rational numbers with respect to the p-adic norm, you get something else. You get what are called p-adic numbers. Right? So there are, if there's different metrics for the space, you can have different completions. But for a given metric, there is a unique completion, I believe. All right, so next up, excuse me, definition. If f is complex function, It's a function from, from the complexes to the complexes, right? Then the limit as z goes to z naught of f of z is equal to L, if and only if what? If and only if for each epsilon greater than 0, there exists a delta greater than 0, such that 0 less than modulus of z minus z naught less than delta implies that modulus of f of z minus L is less than epsilon. You should recognize this. This is the definition of limit that we should have showed you in Calculus 1 for a function of real variables. The difference is that we've replaced absolute value with modulus, all right? And there are all kinds of beautiful theorems, of course. You know the usual theorems, right? Limit laws still hold. All right, so like the limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limit of the quotient is the quotient of the limits. All right. That stuff's all still true. And how can we define continuity at a point for a function? Definition: f continuous at z naught if and only if the limit as z goes to z naught of f of z is equal to f of z naught. Another way to state that is just to give another way to characterize continuity, guys, is just to say for each epsilon greater than 0, there exists a delta greater than 0 such that, and see here, for continuity, all you got to do is just erase the 0 because you actually are considering z naught. When we consider z naught, when we consider continuity of the function at z naught, we have to actually think about the value of the function at the limit point. There is a connection between the world of sequential limits and the world of epsilon delta limits, and that is given by lemma 2.1.17, which says, and this is sometimes useful, the limit of f of z is equal to L as z goes to z naught, if and only if for all zn going to z naught have f of zn going to f of z naught. In other words, a function, if you could find two different complex sequences converging to a given point in z naught such that the values of the function converge to different things or didn't converge to f of z naught, it's not continuous. So half of the proof of that, what I just wrote in red, is pretty easy. The other half is a little bit subtle. I have a link in the notes to the full proof, though. So now, one of the criticisms that's often made of this book we're using, Gamelin, is that he doesn't always write. He does not, like, you will not tend to find an argument like I just gave on the board here in Gamelin. All right? Gamelin doesn't tend to give the full epsilon delta arguments. What Gamelin will do is he'll just basically write the first sentence in my proof, essentially. He'll say, well, because modulus of xn minus, absolute value of xn minus x is less than modulus of zn minus z, and that's less than epsilon, it follows. So like once he gets the central estimate, he'll just say it's clear. So he does not always bind himself to writing the full, the full proof, if you will. In other words, if you were to hand in Gamelin's book as an assignment in real analysis, you would not pass the class, all right, because he is operating at a higher level. he is not. He's assumed that his audience believes that he can fill in the gaps. In contrast, when you're teaching real analysis, the custom of the math community is to have a somewhat distrustful view of students that they could not fill in the gap. And so if we don't see the gaps filled, we tend to go, half credit. So, not me, of course. I don't teach real analysis, so I'm without blame. Okay, so that brings us to the end of the section, which is actually the most important part. And the end of the section here is the part which we actually will be using. And so I'm just going to kind of draw a picture for you. And we'll continue to talk about the end of the section next time, most likely. But I'll do my level best to take a big chunk out of it right now. And so the end of the section talks about what's called, and this is really what I have in the course planner, which is topology. All right, topology of the complex plane. What is topology? So I define some things. For example, I define d epsilon of z naught to be equal to z in the complexes such that the modulus of z minus z naught is less than epsilon, right? I define d sub epsilon with an upper zero on it to be z in the complexes such that 0 is less than z minus z naught is less than epsilon, right? And then I also have d sub epsilon with a bar over it of z naught to be z in the complex numbers such that 0 is less than modulus of z minus z naught, excuse me, no 0, just z minus z naught less than or equal to epsilon. All right. So what you're looking at here, yeah, this is the open disk, deleted open disk, and closed disk. And these are all, radius epsilon centered at z naught. So I should attach that phrase to each one of these to be, complete. Each one of these is a disk of radius epsilon centered at z naught. The first one's open, the second one's deleted, and the third one's closed. All right? So definition, given U a subset of the complex plane, all right, we say z naught, an element of U, is an interior point if there exists epsilon greater than 0 such that the the epsilon ball centered at z naught is a subset of U. If every point in U is an interior point, then U is open. If the complex numbers with U removed, right, is open, then U is closed. So a closed set is one whose complement is open. An open set is one where every point is interior. Now, the definition I just gave for closed, I don't think is the one given by Gamelin. I believe Gamelin gives a sequential definition of closed. All right. There is a sequential definition of closed that you can give. All right. Well, no, like I said, that is what he does. Never mind. My bad. All right, a little bit more. Maybe I'll I mean, excuse me. You can also talk about a boundary point and an exterior point, isolated points. We also like to talk about closure. But I think we're out of time for today, so we'll try to wrap up this section next time. And next time I will give you the definition of complex differentiability. So I've got about a page left in this, which will probably take me 20 minutes, honestly. So sorry I'm a little bit behind. So, I mean, part of the reason for the review of real analysis today, it's more just for your general information than this course specifically, but these are things you want to know as math. We will come back to some of that stuff eventually. It's just it doesn't happen right away.
Yeah, but I didn't know how similar the definitions were.
Oh yeah, they're very similar.